Good evening and a very warm welcome to the Black Hole. Today we are gathered here for screening of a wonderful documentary titled Dear Master. ये documentary Bose-Einstein legacy की वजाहत करती है, जो आप में साइंस के तालिब इल्म है, ख़ास तौर पे जिन्होंने फिज़िक्स पढ़ी है मेरे समेत, उनके लिए तो ये एक ट्रीट टू वॉच है. ये सिनेमैटिक नैरेटिव है that celebrates the intellectual exchange that shaped modern physics, yeah, development of quantum theory in particular. We are very honored and grateful to director of the documentary, Subha Das Mollick साहिबा, और प्रोफेसर पार्था घोष, जो कि इंडियन फिजिसिस्ट हैं, ऑथर हैं, फिलोसफर हैं, साइंस कम्युनिकेटर हैं और फॉर्मर प्रोफेसर हैं एट दी Einstein-Bose National Centre for Basic Sciences. आप दोनों ने वक्त निकाला है, सरहद पार से हमें ज्वाइन किया है. आप दोनों का बहुत शुक्रिया और क्या कहते हैं, स्वागत है यहाँ द ब्लैक होल में. कुछ ही देर में हमें ये स्क्रीन हम नीचे करेंगे तो वो जूम पे आपके सामने भी दिखाई देंगे. स्क्रीनिंग के बाद डिस्कशन होगी, कन्वर्सेशन होगी, जिसमें वी आर ग्रेटफुल टू डॉक्टर परवेज़ हुडभाई जो कि इस गुफ्तगू को आगे बढ़ाएंगे. और हस्बे रवायत, जैसा कि यहाँ पे हमारा कल्चर है कि आप लोगों को भी इस गुफ्तगू में शिरकत का मौका मिलता है. जस्ट उस मौके का इंतज़ार कीजिएगा कि कब हाउस Q&A के लिए ओपन हो. एज़ यूजुअल जस्ट रेज योर हैंड व्हेन द हाउस इज़ ओपन फॉर Q&A, और आप अपना सवाल, अपना जो भी आपका नुक्ता हो वो सामने रखिएगा वंस द माइक्रोफोन इज़ हैंडेड ओवर टू यू. नाउ मैं मज़ीद वक्त आपके लिए बगैर दावत दूंगा डॉक्टर परवेज़ हुडभाई को कि वो इस गुफ्तगू को आगे बढ़ाएं. थैंक यू सर.
थैंक यू. बड़ा अच्छा लगता है कि आप लोग ख़ासी तादाद में यहाँ मौजूद हैं. गो कि इस वक्त इस्लामाबाद में हल्की फुल्की बारिश हो रही है और ठंड है. तो आज हम यहाँ एक बहुत बड़े नाम को, फिजिसिस्ट को सेलिब्रेट करेंगे, और इतना बड़ा काम है उनका कि मैं शुरू ही में आपको थोड़ा सा उसके बारे में बताना चाहूँगा. जिन पार्टिकल से आप और मैं बने हैं, एक किस्म उनमें फर्मियंस कहलाती है, जो एनरिको फर्मी के नाम से मंसूब हैं. एनरिको फर्मी फिज़िक्स में नोबेल प्राइज़ विनर, लेकिन उसके अलावा और बहुत से नए कॉन्सेप्ट्स का मौजूद था. जो बाकी पार्टिकल्स हैं, तकरीबन 50% जो दूसरे पार्टिकल्स हैं, वो बोसॉन्स कहलाते हैं. और बोसॉन सत्येंद्र नाथ बोस के नाम से मंसूब है. सत्येंद्र नाथ बोस ढाका यूनिवर्सिटी में प्रोफेसर था, 24 साल वहाँ पढ़ाया. तो अभी हाल में मेरा जाना हुआ बांग्लादेश, और एक कॉन्फ्रेंस थी वहाँ जो इसको मनाने, इसके 100 साल, द 100th century ऑफ बोसॉन्स को मनाने के लिए की गई थी. तो वहाँ मेरी मुलाकात हुई पार्था घोष से. पार्था घोष से मैं पहले भी मिला था. पार्था घोष इधर इस्लामाबाद आए हुए थे, मेरा ख्याल है कोई 20-25 साल पहले. तो उस वक्त मुझे पहली बार ये पता चला कि पार्था दरअसल बोस के PhD स्टूडेंट थे. उन्हीं के साथ उन्होंने अपना डॉक्टरल डिसर्टेशन लिखा. बहरहाल जब मैं ढाका गया और पहली बार गया तो मेरा दिल बाग बाग हो गया. मैंने कहा देखिए कितनी अच्छी बात है कि एक ऐसा शख्स जो मुसलमान नहीं, हिंदू था, उसे वहाँ सेलिब्रेट किया जा रहा है. तो जब मुझे बोलने का मौका मिला, मैंने कहा कि ये काम तो कभी हम पाकिस्तान में कर ही नहीं सकते, मुमकिन ही नहीं. यहाँ तो हम अब्दुल का नाम लेने से घबराते हैं. तो ये काम तो आप लोगों ने बड़ा ज़बरदस्त किया, और आप लोग 71 में जो किया सो अच्छा ही किया. बहरहाल आज आप ये डॉक्यूमेंट्री देखेंगे, और जैसा कि नैयर ने आपको बताया, उसके बाद फिर कुछ गुफ्तगू होगी पार्था घोष के साथ और सुभा दास मलिक के साथ, जो इस डॉक्यूमेंट्री की प्रोड्यूसर हैं। इसका आइडिया असल में हमें डॉक्टर नकीब ने दिया। नकीब ज़रा हाथ उठाइए। थैंक यू वेरी मच फॉर सजेस्टिंग दिस डॉक्यूमेंट्री टू अस। तो चलिए अब हम डॉक्यूमेंट्री देखते हैं और उसके बाद फिर जो बाकी होगा और जिसमें आपके ख्यालात, आपके सवालात भी शामिल होंगे, उसकी तरफ चलेंगे।
Sie haben als erster den Faktor quantentheoretisch abgeleitet, wenn auch wegen des Polarisationsfaktors 2 nicht ganz streng. Es ist ein schöner Fortschritt. Mit freundlichem Gruß, Ihr A. Einstein.
This is the place where I have spent my childhood and my formative years. This is where, as an adult, I spent hours with my dear friend Nath, poring over the works of Wien, Boltzmann, and of course, Max Planck. Nath translated for me the original German papers into English. The papers were about black body radiation.
Oh wait, let's turn this into a black body.
Wait, I also have something in my bag. How much you will try, it will never be a black body.
Little did I know at that time that radiations trapped in a black body would bring about a turning point in my life.
But the black body is the idealized concept that actually neither reflect nor transmit. Whatever the electromagnetic radiations incident upon it, it absorbs completely. That is the concept of a black body.
Now I'll show you a very simple black body. It's a box here in which there is a small hole. Then you can see that light goes through this hole. Now let me close this box. The hole is still there. Can you see any light coming out of it?
So you need a kind of a closed enclosure. Doesn't mean that inside has to be black. Any radiation trapped inside an enclosure where the temperature is uniform so that you're not allowing, energy flux or heat flux to come from outside or go from inside to outside. So that the system is what we call in thermal equilibrium, then it's a black body.
How do I determine the character of the radiation which is inside and which is in equilibrium at some temperature? Of course, I can raise the temperature of this body. So the characteristic of the radiation inside will keep changing.
You take an iron rod and you heat it. If you get little closer to it, you will feel some heat type of energy is coming from it. If you will increase the temperature more and more, after some points, you will see some dull red color. If you increase the temperature more, you will see some bright red color. If you'll heat more, it will be some white, and if you'll heat more, it will be blue.
Right from radio waves all the way up to gamma rays, you needed specially designed detectors which can detect that radiation. That took a long time.
Let's try to plot a graph which is here. This x-axis is the frequency and the y-axis is it's called radiancy. So experimentally, people observe that this curve is like this type. Okay. So that means at a constant temperature, this black body actually radiates all possible frequencies. But you see, for a particular range, these frequencies, when your body, your black body actually emitting this frequency most likely. If you increase the temperatures, this graph will change. Then the most likely frequency would also shift towards these directions. And that's why this, when you increase the temperatures, the color of your body is changing. Some properties of this black body actually can be described by the Stephen's law. Another important law is the Wien's displacement law, that is saying that nu maximum is proportional to T. Stephen's law was given around 1879. And the Wien's displacement law is given around 1893.
I was born in the year 1894. Nath was born a few months before me. In our colonized nation, Western science had begun to take firm roots.
Both Bose and Saha were in MSc class together, and then they were appointed lecturer in physics by Sir Ashutosh Mukherjee, I think, the Vice Chancellor at that time in Calcutta University. And Saha would translate papers by Pauli and Einstein and explain them to Bose. And then eventually Bose, I think it was Dr. Hartog or somebody who was the Vice Chancellor of Dhaka University, he appointed him as reader. So he moved to Dhaka.
At Dhaka, I initially felt a little cut off. But they had given me an offer that I could not refuse.
Dhaka University had just been set up. So he started teaching a few subjects, which included quantum theory. Now, in those days, quantum theory is nowadays called old quantum theory. Quantum mechanics had not yet come. So let me call them all shots in the dark. The first shot was Planck. The second shot was Einstein, 1905, where he said light itself consists of a stream of particles. We call them photons. The third shot in the dark was in 1913, when Niels Bohr gave his atomic model. At that stage, the main problem in quantum theory was a proper theoretical deduction of what is called the Planck law, Planck's spectrum. And while teaching, he found it very difficult to explain to his students exactly what was happening, because there was no proper theory.
We need some complete theory of this energy density functions or this radiancy, which can actually completely experimentally fit this graph. That expression is actually 8 pi nu square by c cube kt d nu. That is the following expression. Now, what will happen if you plot these things in the graph? Will it actually give you the same experimental curve what we have seen earlier? Let's see what happens. Earlier curve was this one. Now, if you plot this one, what will happen? It will go this way. It is not completely matching. In fact, for the low frequency it is matching, but for the higher frequency it is not matching. So it is called ultraviolet. So this is the range of ultraviolet range. In this ultraviolet range, this classical theory actually completely disagree with the experimental results. So this phenomena is called ultraviolet catastrophe. So this is the big question marks. Why our known classical theory, we are so fond of it, cannot explain this black body radiations. Then we come up to the year 1900, where Planck actually come up with some new hypothesis to explain this curve.
Before 1900, what was known are actually two limits of what we call the Planck distribution law. One is the high temperature limit. So when we say high temperature, we mean that the temperature is much larger than the energy of the light. And in that regime, it is called the Rayleigh-Jeans law. And Wien's law, where the energy density is proportional to nu cubed exponential minus some gamma, a factor, nu over t. But gamma is a constant. So this is at low temperature, high frequency. Now what Planck did, so this matched with experiments in the corresponding limits. What Planck did in 1900 was to actually match these two expressions. And what he got, therefore, a plot of E of nu versus nu at different temperatures. And so this curve roughly looks like this. So this is Wien, and this is Rayleigh-Jeans, okay? The low frequency and the high frequency behavior. And with temperature, the maximum would shift. So this is Planck in 1900.
I mean, he then finally came to the conclusion that the material of which the black body is made, the walls, they do not absorb and emit radiation continuously, but in discrete quanta. Okay, so this was a very bold hypothesis. He said it was an act of desperation. But even then, to get to the final step, he had to assume something or the other. So Planck's derivation was not a very satisfactory derivation. His formula was perfect. But to get to the formula from some theoretical basis, there were a lot of problems.
In the year 1900, I started going to school.
Then comes Einstein in 1905, the famous paper that we know as photoelectric effect.
The emission and absorption process is discrete. Light itself consists of a discrete set of energy packets. He called them light quanta. Today we call them photons. So the idea of photons was that of Einstein. Einstein's light quantum hypothesis was not accepted by many physicists in the West because there was an apparent contradiction between light being a stream of particles and light also showing interference effects, which is typical of waves. In fact, that gave birth to what is called wave-particle duality.
He assumes that the electromagnetic radiation is a gas, is an ideal gas of what he called light quanta. If there are n such light quanta in the room, in the black body, then the total entropy will be nth power of that volume. What he gets is a remarkable expression that if there are n such quanta, then the energy is n times h nu. So today we know it as the energy quantization formula, where n is the number of, we call them photons now, h is a Planck constant, and nu is a frequency. So this is the remarkable result. And from this, actually, he derived what the Planck constant should be. And then Millikan measured it 8 years later and got complete agreement with Einstein. That 1905 Einstein was like a karma yogi Einstein. Okay, he is deriving things which are matching with experiments. He's calculating the Avogadro number, the Planck constant, etc. 1905 is considered the miraculous year of physics because Einstein wrote 3 momentous papers. What are these papers on? One is a theory of the Brownian motion, which is an explanation some 80 years later of something that was observed by Robert Brown, an Irish medical practitioner whose hobby was to look at things with a microscope designed by himself. Similarly, then comes the other paper, which is known as photoelectric effect, but actually it was Einstein's analysis of the Planck radiation law, and the outcome was the photoelectric effect, which basically says that if you shine light on a metallic plate, then electrons get ejected. And so only in the case of special theory of relativity, Einstein did not have the benefit of many experiments, though Michaels and Morley were there. So he did some Gedanken experiment, thought experiments of what would happen if he were to travel up and down in a lift.
In 1905, Bengal was partitioned. We took to the streets in a protest march and tied Rakhis on our friends' wrists, both Hindus and Muslims.
What Einstein did in 1905 is really not a derivation. Einstein was putting pieces together of Rayleigh jeans, Wien, and then putting them in juxtaposition with the Boltzmann idea of thermodynamics, and then actually getting a value of the Planck constant, etc. Bose wanted to derive this. So Bose was struggling with that.
And while teaching, he found it very difficult to explain to his students exactly what was happening because there was no proper theory. And so he was grappling with these ideas.
Thereby, Nathanson, Ehrenfest, and Planck himself were bringing in new perspectives. But there was still something amiss.
But what is very interesting for me is the complementarity of research with teaching. How by teaching a class, you get ideas of research. And this is a classic example because students were constantly asking, "Sir, how do you derive this Planck radiation law?"
So imagine a young teacher in Dhaka confronted with all these possibilities, trying to teach this to his students. He was very dissatisfied. And he found that the main problem with all these derivations is that Planck's law consists of 2 factors. The first factor is 8 pi nu square over c cube. The next factor is h nu divided by exponential h nu divided by kt minus 1. Now, it's the second part whose derivation all these people, the great physicists of the time, they were trying to give an explanation of that. But as far as the first factor is concerned, they took it from classical theory. Classical is a number of modes in a volume. This Professor Bose found very unsatisfactory, that you should use both classical physics and partly classical physics, partly quantum physics. So he said, no, I must give a derivation, completely quantum theoretic derivation of the whole formula. And that is where his genius was expressed. He gave a derivation.
What Bose did in 1924 was quite revolutionary. He showed us how to count what we call now fundamental particles. This was a new method altogether. And so what came out of it is a kind of a new statistics. While Einstein was looking at the macro physics of entropy, etc., thermodynamics, Bose wanted to go to the micro world and go and do how to do this counting.
He sent this paper to Philosophical magazine. They probably rejected it. Then he wrote a letter to Einstein.
Respected sir, I have ventured to send you the accompanying article for your perusal and opinion. I'm anxious to know what you think of it.
You will see that I have tried to deduce the coefficient 8 pi m nu square by c cube in Planck's law, independent of the classical electrodynamics, only assuming that the ultimate elementary region in the phase space has the content h cube.
I do not know sufficient German to translate the paper. If you think the paper worth publication, I shall be grateful if you arrange for its publication in Zeitschrift für Physik.
Bose's first contact with Einstein was when he and Meghnad Saha were translating Einstein's papers on relativity, which were written in German, into English. So he wrote asking for his permission. And Einstein, of course, gave them the permission, but I believe he put a clause that this should be only meant for buyers in India.
I do not know if you still remember that somebody from Calcutta had asked your permission to translate your papers on relativity in English. I was the one who translated your paper on generalized relativity. Yours faithfully, S.N. Bose.
And then he sent a kind of a manuscript. Interestingly, the details of the manuscript are not known. What was known is what Einstein communicated.
Einstein had assumed that photons travel like ordinary particles. They're all independent of each other. Then immediately, several scientists pointed out, but then you will never get Planck's law. Planck's law requires some other way of propagation. And this is exactly what came out of Professor Bose's work, that these photons are not like ordinary billiard balls. They are what's today, in today's language, called indistinguishable.
So consider about a two box labeled with 1 and 2 and consider the two distinguishable particles. Now, according to the Maxwell-Boltzmann statistics, what are the valid states? Now, if they are bosons, like they are not distinguishable, they are indistinguishable, then the valid states would be
He was the first one to give a complete theoretical derivation of the entire Planck formula, including the first factor. Now, in the first factor, what he showed was that it gives the number of possible states of a photon. Now, once you know, and that is fixed, now once you know the states, you can start distributing photons in them. If I interchange these two balls, will I get a new state, new arrangement? know why, for this to give rise to a new arrangement, I need to have another box. Let me put it here. And then these two balls I can interchange and put there. So you will have one like this, another like that. So, but I need another box, but I don't have that. So by interchanging these two, I don't get a new state. This is indistinguishability. And this is inevitable in the way Bose did it.
Einstein saw something deep in this.
Lieber Herr Kollege, ich habe Ihre Arbeit übersetzt und der Zeitschrift für Physik zum Druck übergeben.
But he commented that he was certainly the first person to give a proper quantum theoretic derivation to Planck's law, except that you introduced a factor of 2, not entirely logically. So Einstein then was so excited that finally his concept of photons was given a very strong theoretical justification. He went gaga. And he wrote 3 papers within 6-7 months. So he applied it to material atoms. And then he was absolutely stunned, because when he applied it to material particles, he found that material particles should have a wave nature. Now he had himself proposed that something which had a wave nature, light, should have a particle nature, wave-particle duality. Here is a case when application of Bose's statistics to material atoms tells you material atoms should have waves, a wave character. So he was stunned, and he immediately remembered that some French fellow called Louis de Broglie had sent him a thesis about a year back, where he had also proposed that material particles, in analogy with Einstein's theory, that if photons have a wave character or where light has particle character, then something we know as particles should also have a wave character. Now, he did it by pure analogy. Einstein was not impressed. He put away the paper. But when he saw Bose's paper, that came back to him and said, what a great idea. It's not just an analogy. It is actually there because of statistics. So he wrote back to de Broglie's thesis supervisor, Paul Logevin, and asked for a second copy, which he sent him. And then Einstein started writing these papers, explaining Bose's statistics, bringing in de Broglie's hypothesis that material particles should have a wave nature. And finally, he came to the conclusion that at very, very low temperatures, below a certain critical value, such Bose gases should condense into the lowest possible energy state, which nowadays called Bose-Einstein condensates.
So then what Einstein did, he then calculates the pressure, and he finds that the pressure is lower for identical gas of bosons. I'm calling them bosons already because the name came later, than if these particles were distinguishable. And so that gave rise to the idea of a condensation, that so many bosons would flock together. Helium-4 will, at sufficiently low temperature, will then go into a condensate. And this is what we call today Bose-Einstein condensation, which was discovered experimentally many, many decades later.
And then, of course, later on, as we all know, the wave character of electrons were actually seen in an experiment which Davis and Germer had carried out. And then the question came, if material particles have a wave nature, what is the equation of that wave? And eventually that equation was written down by Schrödinger, and that gave birth to what we call today quantum mechanics. So you see how Bose's work stimulated the development of quantum mechanics.
Es ist ein schöner Fortschritt. Mit freundlichem Gruß, Ihr A. Einstein.
In October 1924, I set sail for Europe. I was on a 2-year study leave granted by University of Dhaka. In Paris, 17 Rue de Somerard was a favorite nest for Indian students, including the ones involved in the nationalist movement. Madame Curie graciously allowed me to work at her Radium Institute. But I had to brush up my French before she took me in. I also attended Paul Langevin's lectures and worked in Maurice Debray's X-ray crystallography lab. But my heart was set to meet Einstein in person.
The first paper he sent, as I already said, to Einstein, which Einstein immediately accepted and told the entire story. But within a very short time, perhaps about a couple of weeks, he also sent his second paper.
Dear Master, my heartfelt gratitude for taking the trouble of translating the paper yourself and publishing it. I just saw it in print before I left India. I have also sent you, about the middle of June, a second paper entitled Thermal Equilibrium in the Radiation Field in the Presence of Matter. I'm rather anxious to know your opinion of it, as I think it rather important. I shall wait for your decision as well as your opinion on my second paper here in Paris. Yours sincerely, S.N. Bose.
In the first paper, you will find something extremely striking. There is not a single reference. Whereas in the second paper, you will see references to all the previous work, which means he actually wanted these two papers as a kind of single paper in two parts. So the first paper was only about the intrinsic property of radiation in equilibrium. And he showed that Planck's formula follows not because light is getting emitted or absorbed by anything, by its own nature. Because of photons and their statistics, you get Planck's law. But in the second paper, he introduced matter. And again, he showed that it doesn't matter what the mechanism of emission and absorption is. You always get Planck's law. And then he showed that all the previous attempts by everybody followed as special cases of his most general formulation. This was the first part of the second paper. And Einstein translated it and published it.
Dear colleague, thank you sincerely for your letter of 26th October. I am glad that I shall have the opportunity soon of making your personal acquaintance. Your papers have already appeared some time ago. Unfortunately, the reprints have been sent to me instead of you.
But he had a second part, in which he considered a specific case, the Einstein case of two-level atoms where energy is absorbed and emitted. And Einstein had said the emission has to be of two kinds: induced emission and spontaneous emission. The spontaneous emission is the one which gives rise to Planck's law. Now, Bose showed that it's not, Bose's argument, general argument was that it's not necessary to split the emission process into two parts like this. Emission is emission. So, since everything follows from the new statistics, we should not separate these two. If we assume induced spontaneous emission, then from the formula you will see that there is an induced emission also, and also vice versa. He didn't show the vice versa case in this paper. Now Einstein objected to this by putting this time an adverse note. He published the paper but put an adverse note that I do not agree with Bose in this particular respect. So he was very perturbed. Now he held Einstein in great esteem, so he started thinking, what could be the problem? Why is Einstein objecting like that?
Revered Master, I received your kind note of 3rd November. I have been thinking about your objections all along, and so did not answer immediately. It seems there is a way out of this difficulty. I have written down my ideas in the form of a paper which I send under a separate cover. It seems that the hypothesis of negative Einstellung stands, which reflects the classical behavior of a resonator in a fluctuating field. The views about the radiation field, which I have ventured to put forward, seem to be very much like what Bose had recently expressed in the May issue of Philosophical magazine. But it is only a guess, as I cannot say honestly that I have understood all he means to say about virtual fields and virtual oscillators.
So he wrote a third paper, which he also sent to Einstein, but Einstein never even responded to it. So these incidents actually dampened Bose's spirit quite a lot. Now, Bose went to Berlin in 1925 and met Einstein. They discussed all these problems.
In 1925, Einstein was the director of the Kaiser Wilhelm Institute. Berlin was exploding with groundbreaking discoveries, and Einstein was the center of gravity of all the debates and discourses around these discoveries. Dear Jacqueline, everybody seems to be quite excited in Berlin about the way things have been going on with physics. On the 20th last, Heisenberg spoke in the colloquium about his theory. Then, in the last colloquium, there was a long lecture on the recent hypothesis of the spinning electron. Perhaps you have heard about it. Everybody is quite bewildered, and there is going to be very soon a discussion of Schrödinger's papers. Einstein seems quite excited about it. The other day, coming from the colloquium, we found him jumping in the same compartment where we were, and forthwith he began to talk excitedly about the things we have just heard. He has to admit that it seems a tremendous thing, considering the lot of things which this new theory seem to correlate and explain. But he's very much troubled by the unreasonableness of it all. We were all silent, but he talked almost all the time, unconscious of the interest and wonder that is exciting in the minds of other passengers.
But Einstein was at that time working out his three papers based on Bose's work. It's quite strange that Bose was present there. He was a young man. He was not asked to collaborate. Now, why that happened, I do not want to speculate, but that is a fact. Although Bose was not asked to actually collaborate, there is some evidence that Einstein had asked him to calculate something, namely that by considering fluctuations of these particles in small volumes, what would be the nature of the fluctuations? And there is, we got a piece of paper from the Einstein archives written in Bose's hand, where you can clearly see that Bose had calculated the fluctuation in which it shows two terms. One, the wave-like term, the other, the particle-like term. So the fact that Bose statistics gives rise to these two terms, Bose also knew. And that paper exists in the archives of Einstein.
I mean, Gamow wrote 30 years of physics that shook the world. And so this is the end of the 30 years. I mean, from 1920 onwards, I mean, of course, Niels Bohr was there in 1913, but 1920 onwards up till 1928, 1930, it culminated with the Dirac equation. There was a flurry of activity, but I don't think Satyendra Bose continued to work on quantum mechanics per se in great depth or detail, but he had many other interests, as I said before.
Nobody has seen the third paper. Bose never kept a copy, Einstein didn't keep a copy, so we don't really know what was written, except that there is a letter from Bose to Einstein saying he has shown this paper to Professor Lorgemain, who thinks it is worth publishing, but nevertheless I am asking for your opinion. And that opinion never came. So one day he told me what was the difference between the third paper and the second paper. Now in the second paper he had said that if I only assume the emission process to be spontaneous, then the induced part also automatically comes from the formula itself. In the second, since Einstein had objected to it, he changed the position. He said, okay, let's now say that there is only induced emission. Then the spontaneous part comes automatically. You don't have to put it in by hand as Einstein had done. Einstein's idea was that spontaneous emission is an intrinsic property of the atom. Bose had a different idea. He said, no, it's a consequence of the statistics. So apparently one day, Einstein gave him a piece of his mind. He told me, Budo used to talk in a very strong fashion, and he told me, supposing there were only one hydrogen atom in this universe, and it was in an excited state, don't you think it will radiate and come down to the ground state? In other words, spontaneous emission should be there. So Bose said, I was so awestruck by his attitude and so on. He didn't say anything, he came out of the room. But he said, as soon as I went out, the answer flashed in my mind. He said, I should have told him, sir, if there were only one hydrogen atom in the universe and nothing else, then neither you will be there nor I. So let's not talk about such a situation.
I often dropped into Einstein's villa. Any discussion with him was always stimulating.
Sagen Sie nun, wollen Sie wirklich, dass die Engländer ihr Land verlassen?
Of course, we all want to determine our destinies ourselves.
Suppose there was a button in front of you, and all the Englishmen would leave India if you were to press the button. Would you press it?
If God were to grant me such an opportunity, I would not hesitate even for a moment to press it.
Really?
Why do you Jews want to establish a new Israeli state? Even you seem to be fairly inclined in its favor.
I have understood what you're saying. It is an emotional matter and cannot be explained by logic.
Two years in Europe seemed to pass like the blink of an eye. Before I knew it, I was heading back home. But there was a different kind of excitement awaiting me at Dhaka. The excitement of building a modern department of physics at the university.
Bose was very popular there. And, there were very famous Bengalis there, like Professor A.K. Das Gupta, the famous economist, who was a teacher of Amartya Sen, Shokhamay Chakraborty. As you know, Bose had many other interests. He played Esraj, and he also was a great friend of the poet Bishnu De, the great artist Jamini Roy. Bose was like that. He used to interact socially with a lot of people. He was a very popular figure in Dhaka. Bose dabbled into many things. He had interest in chemistry. He had interest in X-ray crystallography. He also, I believe, was the first proponent of the fact that Bokrish or hot spring will emanate helium, both helium-3 and helium-4. And that idea was taken up by Dr. Shyamadas Chatterjee and later on by Dr. Bikas Sinha and the group in the Variable Energy Cyclotron Center. But originally it was S.N. Bose's.
In 1935, while I was still in Dhaka, I wrote a popular article on Einstein for the Bengali magazine Porichoy. 30 বৎসর আগে আইনস্টাইন যে প্রবন্ধে আপেক্ষিকবাদের সূচনা করেন তাহা পদার্থবিজ্ঞানে নূতন যুগের অবতারণা করিয়াছে। জড় জগতে ঘটনাসমূহের বিবৃতির জন্য বৈজ্ঞানিক যে দেশ কাল প্রক্ষেপ ভূমির পরিকল্পনা করেন তাহা দর্শক নিরপেক্ষ নয়। In 1935, Einstein had decided to settle down in New Jersey in USA with a position at the Institute of Advanced Studies at Princeton. Staunch anti-Semitic measures in Germany prevented him from returning to Berlin.
Bose was more of a mathematician. Einstein was more of an observer of nature, a physicist, very intuitive man. Bose was a very good student. He studied in MSc, what at that time was called mixed mathematics, he and Meghnad Saha. He stood first, Saha came second. Einstein was pretty bad in his school studies. Bose is more driven by mathematical logic, while Einstein was governed and driven intensely by phenomena.
Professor Bose never could accept Einstein's criticism of his second paper. Now, he has said this to many of his students, including myself. But since he could not come up with a very satisfactory answer himself. He never published anything. But he told me definitely that I should look at his old papers and see if I can give them any modern interpretation. তুই দেখিস তো বাবা আমার পুরোনো পেপার নতুন কথা আছে।
I would say that if you try to find a comparison of that kind of a person in our country who was so intuitive and is a close observer of nature, of phenomena, the only other person I can think of is Rabindranath Tagore.
We were planning to celebrate his centenary, birth centenary, when I was then in Bose National Centre. I was going through various journals and so on at the Indian Association for Cultivation of Science, and I accidentally came across a paper of C.V. Raman and Bhagavantam with the title Experimental Determination of the Photon Spin. I was intrigued. I started looking at it. And then I was amazed because they, right at the beginning, say that this idea was given to them by Bose. And they actually did an experiment to show that Bose was right. In fact, that was the first proper paper in which photon spin was discovered. But in the West, it's been ignored. Now, of course, after I have been saying this, you will see that people have started referring to that paper. So this is how Indians have been, ignored in the past, even a man of Raman's stature.
Bose's works on general relativity. See, there is another letter from Einstein.
In the mid-50s, he suddenly got interested in Einstein's unified field theory. See, Einstein had given his famous general theory of relativity, which was a theory of gravitation. And of course, we have Maxwell's theory of electromagnetism, light. He wanted to have a single theory which will give you both this, as well as would explain the quantum phenomena in one stroke. So that was called the unitary field theory. So Einstein was attempting to do that. And in a particular version, he had many ideas to do it. In one of those versions, there was a set of equations. I will not go into the details. It was a set of 64 equations which were all coupled to one another. And it was very, very difficult to solve. At that time, Schrödinger also was interested in the same problem, and he wrote a book called Space-Time Structure, in which he made a comment that most probably these equations have no exact solutions. So we have to somehow try approximations and so on. So one of Professor Bose's students, I don't know exactly who apparently showed that part of the book to Professor Bose. So what I've heard is, well, this was not before my time. So Professor Bose said, oh, Sahib boleche hoy na. The Sahib had said, it can't be done. Okay, leave it with me for some time. And within a very short time, he found exact solutions. So he wrote about 5 papers on various aspects of unified theory. Except one, all were published in French, because he was very good in French. And he was corresponding with Einstein. So Einstein, in one letter, says that it seems you have worked very hard and penetrated deep into the subject. But I have my own ideas. That I think what I have done is the most you can do today. So Bose was preparing to write yet another paper. And this was around 1955, when it would be 50 years of the special theory of relativity. So a special international conference was being convened somewhere in Europe, where Einstein would come, and Bose was also planning to go there. Actually, he did go there. But before the conference, Einstein died. So Bose was, of course, very eager to meet Einstein and talk about his latest paper. So someone went and told him that Einstein had passed away. Apparently, he just froze. And after a while, he took out a copy of the paper, tore it up, and threw it into the waste paper basket. And after that, he never wrote any further paper in physics.
To the teacher who removes all my doubts, veils my vision into a unity, and thus enables me to gaze on secret knowledge, to that one my homage.
Did you see inside? So most of the letters that Bose wrote to Einstein, he used to address him as a master or sir.
Yes.
Probably he might be the only person who used to address him as a master.
I think they have very unique bond in between them. And it's very hard to find in the history of science such kind of pair like Bose and Einstein.
Bose became famous because Einstein recognized his contribution. And his name got linked to that of Einstein. Here was a man born in pre-independence India. He goes to teach in Dhaka, does brilliant piece of work. It absolutely shook the world because of Einstein's appreciation of it. But then, at the end of the day, he was also disappointed because Einstein ignored some of his ideas. But that's the way life is.
Well, that was fabulous. We will now engage with Subha Das Mollick and with Partha Ghose. Subha, who produced the movie, the documentary, and Partha, who was the star. So it's wonderful to see you, Subha.
Thank you. Thank you for screening the film and inviting me.
Well, it is absolutely our pleasure. Tell us a little bit about yourself. You're not a physicist. You are known for your filmmaking, for your documentaries. Tell us a little bit about your career.
No, actually, I have been a physics teacher for a large part of my life. But then in 1995, my career track changed from physics to media. But still, once my interest in physics was there, and as a media person, as a maker of educational films, I have made quite a few science-based films also. So that's the thing. So I have a physics background. I have taught physics for several years at school and college level, mainly college.
I see. So that's why it wasn't too difficult for you to conceptualize this film.
Yeah, I guess so. Yes, yes, yeah.
How you certainly put in a lot of resources into this because there are the shots from Germany and there seems to be a lot of archival footage as well. How
Yes.
long did it take you to make this and what sort of investment went into it?
See, archival footage, a lot of it I got from the Bose National Centre for Basic Sciences. They have an archive, and so a lot of pictures, etc., are there. Some are, particularly the Dhaka shots, I borrowed from an earlier film produced by Vigyan Prasad. So I took their permission because this was a self-produced film, so it's a rather low budget film, so I did not invest in going all the way to Dhaka to take the shots, but Vigyan Prasad allowed me to use the Dhaka footage from their films, so which I have used here, and some, the Paris and all that, so that I have a very good animation artist, so I did animation, means I took still images and I got all that animated, you through the help of a friend of mine who is very good at doing this sort of animation. Snow falling and in the Eiffel Tower and the vehicles, old vehicles, 20s vehicles passing along the streets, all that was animated. For taking some still pictures, I got them animated.
Well,
So that's what.
that's really creative. I actually thought, I mean, I don't know much about these things, but I actually thought that was snow falling in Paris with the backdrop of the Eiffel Tower. But it was this clever AI generated stuff, huh?
No, but this was not
Okay.
AI actually. This was done by an animation artist. This was not AI generated. Many people think this is AI generated, but this is not. Maybe AI can do it more easily, but here the artist actually did it using his software.
Okay, good. So
Yeah.
hang on for a bit while we talk with Partha and then it'll
Yeah,
be
yeah,
open.
sure.
Okay. Partha, are you there?
Yes, hi.
Oh, okay. So let's have your
Hello,
full screen.
Pervez.
Lovely to see you. How have you been?
Lovely to see you. Yeah.
Good, good, good. So, look, if I was ever to stand before Einstein, my knees would start knocking and I'd probably fall to the floor. How did it feel for you to be before Satyendra Nath Bose? You were his PhD student. So, tell us a bit how you encountered him and what did it feel like to be before the most famous, or maybe the second most famous physicist in India at that time?
Well, it all happened by kind of accident. I never planned to study under him. I didn't even ever imagine I would ever see him. But what happened was, Bose had a close friend who was a poet, Vishnu De, who happened to be my father's uncle. So he knew me from childhood. And his son, Jishnu, is also a physicist. So one day, Jishnu and his sisters used to address Bose as Jetu, which means the father's elder brother. So he said, "You haven't seen Jetu, come along with us." So one fine morning, I went along with them and to see the great man, and he was sitting on his bed, a benign old gentleman. I was introduced to him, and then they were chatting among themselves. I was just
What year
sitting
was this?
and watching them.
What year was this?
Suddenly he turned to me
No, what year
and
was this,
said in
Partha?
Bengali, "তুই আমার সঙ্গে কাজ করবি?" That means, "Tu," I mean, he addressed me as "Tu. Would you like to work with me?" I was absolutely stunned. For a second or so, I didn't know what to do because I was already working with someone else in the Saha Institute of Nuclear Physics. And here was Bose asking me to to study under him. And somebody from inside told me that there's only one answer, just say yes. And I said yes. And that's how it happened. So,
But you
well,
have
I
to
mean,
tell.
he was
Hang on 1 second. What year was
Yeah.
this? Because we need the context. So how old were you, and how old was he, and what year was this?
Well, I was about 23, 24, and he was, he was born in 1894, so I'm talking of 1963. So he was about,
He was in his
he
60s.
was in his early
He was in his
70s, let us
60s,
say.
yeah.
Yeah. And he was retired already then. But he was made a national professor of physics. So he had his own unit. He got money from the government of India to do some experiments with this helium extraction from some hot water springs. And he also could employ some junior and senior scientists. So I was employed as a junior scientist under him. But he was such a loving person, such a warm person, such an informal person, that actually I had no problem with him, except that whenever I saw him, I said, oh my God, this is the great man.
Did that awe stand in the way of your doing good work in physics itself? Were you so afraid that you wouldn't challenge him, question him, ask for explanations?
This is a difficult question. I must admit that I was very young. I had just started my research. So I was very immature. And therefore, I regret now that if I had today's maturity then I would have asked him many, many questions. But I lost the chance. He more or less allowed me to do whatever I liked to do. But he would call me. So there was another person in his group who was a senior scientist, Dr. Purnangshu Roy. He did his PhD under Salam at Imperial College. So Bose had asked me to keep in touch with Roy for most of the time, and that's what I did. But he would call me from time to time and ask me for progress. For example, when I said I was interested in symmetries, because at that time the octet model had come, the SU3 symmetry was there, and people were talking about Lie group classifications. So I said, I want to learn all that. And he said, fine. So he got a friend to send him Cartan's original thesis in French. And he said, keep it. I didn't know any French. But fortunately, someone called Fronsdal had written a very wonderful summary of Cartan's work in English. And I studied that with a friend, Siddharth Sen, who's now in Dublin. The two of us studied that very thoroughly. So that's how he inspired us. I mean, that's one way. The other thing that he kept harping on was, of course, his differences with Einstein. And I really couldn't do anything at that time, but that made me, later on in life, to switch to foundations of quantum mechanics, which I have been doing since 1989 or so, mainly with my younger colleague, Dipankar Home.
Okay,
So
now
I switched from quantum field theory and particle physics to foundations. And that was an influence of Bose.
Partha, we saw in this documentary that, and everybody, I think, will appreciate the fact that Bose did something very fundamental in physics. That idea of the photon being a particle which has spin and which is gregarious. meaning that it likes to be with other particles. That's really fundamental. And only a few such fundamental discoveries have been they've changed the character of physics. Nevertheless, he did not get a Nobel Prize. Do you think that he should have got one? Did he think, more importantly, did he think that he should have got the Nobel Prize? He didn't. Why do you think that happened?
Well, as a physicist, I'm sure you will agree that he ought to have been given a Nobel Prize. I think no physicist today would ever doubt that. But why it didn't happen is something I cannot really answer satisfactorily. All kinds of influences and all kinds of considerations must have been there. But I personally feel that if Einstein had exerted his influence a bit, then I think it would have been given. But Einstein somehow rather moved away from this particular field of statistics. That is his papers, the three papers which followed Bose's, were the only three papers he ever wrote on quantum statistics. And if you look at his autobiography, which he wrote, I think, around 1954 or 53, it's there in that book edited by Schilp called Philosopher, Scientist Albert Einstein. So if you read that, when I read that, I was very shocked that there's not a single mention of his own work or Bose's anywhere.
Well, we do
I
know.
don't know. Maybe he lost interest in this kind of work or not.
No,
I don't
it might
know.
be more fundamental because Einstein started doubting the validity of quantum mechanics itself as a complete theory of physics, and
Exactly.
then his search for hidden variables, and then his famous paradox, which he came up with Podolsky and Rosen, which tried to make fun of quantum mechanics, but which actually turned out to be super important, and which today might be the reason that we think of quantum computers. So that his move away from quantum mechanics, his search for determinacy, might have might have a role to play in this. But okay, but I want to come back to my question. Was Satyendra Nath Bose bitter about not being sufficiently recognized by the Nobel Committee, or was his name ever proposed by anyone?
Yeah, actually, his name was proposed 5 times because this a special issue of this Bengali magazine Gyan Bigyan has come out to celebrate this 100 years of Bose-Einstein statistics. So there is an article. I'm forgetting the author's name. I have to check it. Who has given a full account that 5 times his name was proposed for Nobel Prize, but the Nobel Committee had its own reservations, so they rejected. So that whole article is there. So his name was proposed.
Do you know do you recall who the proposers were, perhaps?
Yeah, which there I have to check that. I can tell you, not often, but it's all there on record. No, it's a Bengali article, so I'll translate in English and I can share with you. Not immediately, but yeah, I can share with you.
Okay, that's interesting. But
But one thing, when this Bose-Einstein condensate was finally achieved in the laboratory, that was, of course, the final, experimental proof of Bose-Einstein statistics. So then neither Bose was alive nor Einstein was alive. And Nobel Prize is not given posthumously.
Okay, now my last question before we go to the audience, and actually this is a kind of an objection. I heard Partha saying in the movie that there are no exact solutions to the Einstein equations, which are a set of 64 coupled equations with each other. And when Bose saw this, he said, let me think about it, and then he came up with an exact solution. But wait a minute, that's not true. Because in 19 17 or 1918, and this was Schwarzschild who came up with an exact solution of Einstein's equations with spherical symmetry. And there's nothing wrong with that solution. That's an exact solution. So why, Partha, did you make that statement that there was no exact
No, no.
solution?
Well, Pervez, this was not general theory of relativity. This was unified theory.
Okay.
Yes.
All right. Okay.
A particular version of the unified theory which had torsion in it.
Okay. The unified theory was a dead end anyway, so never went anywhere. So now I will open the floor for questions. Who would like to ask the first question?
Thank you for this very amazing film screening, because you also are a professor, and Dr. Partha is also here. So I will share my experience when I started my research, and I was very motivated, and I wanted to work in the lab and be a real scientist. And when I started to work in the lab, and my supervisor was he was a senior scientist, and at a government institute, and I proposed what I want to do, and he said, "Wait a minute, take it easy. Do you want to become an Einstein? I will tell you what you should do." And he taught me a trick: make an Excel sheet, read 10 papers, and in the one column, write down the title of the paper. In the one column, write down the methodologies, and in the one column, write down the results. And then mix match, and new papers comes out.
Okay, look, that's a person like that,
Yeah.
like your professor,
Yeah.
should be immediately fired.
Yeah.
And all the money that he has received as salary should be, then he should be forced to repay that.
Yeah.
So your professor is a fraud.
So-
Let's go to the next question.
So my question is how to keep this spirit alive.
That I think Professor Partha Ghose can answer best. Because he is an excellent science communicator, also science popularizer. So, Professor Ghose.
What is it?
That how to keep this is, even though you have overbearing research guides, who don't allow creative thinking, how to keep this creative juices flowing and how to keep this spirit of inquiry alive.
That's very difficult. If you have a boss who's of that kind, then the only solution is to just leave him and go to somebody else who's more friendly. What else can I say?
Yes.
My name is Nakeem, Dr. Nakeem. मैं mathematician हूँ. Maybe उर्दू में बात कर लेते हैं. कुछ
I'm not sure he'll be that they're both.
is this
equal.
okay to if I speak in Urdu?
Professor
Partha?
Partha Ghose, should he speak in Urdu or English?
I don't understand Urdu, unfortunately.
Okay,
So if I am to answer the question, it has to be in English.
Okay, so the first, it's a wonderful story. I really liked it. Actually, I think 1 or 2 months ago we screened actually plays here about Einstein. It's called The Light Falls, and the obsession of Einstein with the light. So I think that was one of the reason YouTube and the artificial intelligence actually showed me your
Film, yeah.
this film on YouTube, and I immediately sent an email to Hoodbhoy that I really liked it, and we should have a screening of it here, and I really
Thank
like
you.
to see all this. I think I'm a mathematician, and we know a similar story of Ramanujan. The Ramanujan with G.H. Hardy, and would you like to make a similar story or film about Ramanujan?
On Ramanujan, there are already some very nice, very good films already made
Yeah, yeah,
by a friend of mine. He has made more than one film on particularly Ramanujan Hardy relationship.
yeah,
So, and those films are available. I mean, I can share the links with you.
yeah,
So,
yeah.
those films are made already.
Yeah, but they are films like. Is there any documentary just like this one?
Yeah, documentary. And yes, it's not a. I'm not talking about fictionalized film. That is also made, but I'm talking about documentaries only.
Okay, okay.
I'm talking about documentary. This Nandan Khudiadi. His name is Nandan Khudiadi. So he made the first documentary on Ramanujan and how Hardy discovered Ramanujan and brought him to limelight, etc. That was at least 30 years back, if not more, at least 30 years back. Huh. So I used to live in Bombay at that time. So we had watched it in St. Xavier's College, Bombay. After that, he made more. He made sequels also. So Nandan Khudiadi has become a Ramanujan expert. And all his films are documentaries.
Okay, that's great.
And they're there in the public domain. So I can look for the links and I can share with you.
Okay.
Okay, and one more question with from Professor Partha. I was thinking about this Solvay conference. It was also shown
Yeah.
in the documentary. Why he didn't attend any conference like Solvay conference?
Yeah.
Yeah.
Particularly the 1927
Yeah.
Solvay.
Well, I'm not quite sure. Maybe he was not invited.
Okay.
Yeah.
And the last question, what about this last paper? I think which he, I mean, he didn't work on after that.
Publish.
So who did that work and what happened to that research after that?
You mean the third paper? The third paper on that never got published.
Mm-hmm.
That's the paper you are referring to, is
No,
it?
the last one, I think Professor.
Or is it the one who tore up on unitary field theory? That
exactly.
one.
Yeah.
Okay.
Nobody actually followed all that up. That is very unfortunate. But if you're interested, I'll tell you something about myself. Because he repeatedly asked me to look at his papers to see if they have any modern relevance. He said, forget about the old thing. I think my papers have something new, and try to understand that. And eventually, I think I have seen what was very original and why Einstein rejected it. And the idea is that in that second paper, he had actually proposed that the interaction of light and matter itself is probabilistic. His idea was that in classical theory, if charged matter and electromagnetic waves meet, then they will inevitably interact. The probability of interaction is precisely 1. However, if you read his second paper carefully, you will see this written there explicitly, that the essence of quantum phenomenon, the fact that the electron is going round in an atom and therefore is accelerated and should radiate, does not radiate, shows that the essence of quantum physics is that even when matter and radiation come into contact, there is a finite probability that they will not interact. And he found an expression for that probability. Therefore, he was introducing probability in a very intrinsic way into the theory. And Einstein always believed that God does not play dice. So Bose was that radical. Unfortunately, he did not team up with Bohr and Heisenberg and so on. If he had, then the history probably would have been different. He had to come back to Dhaka because Dhaka University had given him a lot of money to go and pick up the latest techniques so that he could return and build the department. And also, I think his respect for Einstein was so deep that he just gave up. But he didn't actually give up, but he kept wondering. And recently, I've come across some papers which were actually written a long time ago, late 1960s, by someone called Edward Nelson. And he has shown that if the fundamental processes are random, like Brownian motion, then you can actually deduce the Schrödinger equation from there. That's wonderful. It's an idea which it has really struck me, and I'm now working on that sort of thing. And I think this is the kind of idea which Bose had in his mind in an essential form. But of course, all the mathematics, like the Ito calculus, stochastic things, all these things did not exist in his time. So he couldn't use all that.
Partha,
But now we have this kind of a possible solution.
Partha, let me try and give a partial answer to the question that Dr. Naqib raised over here. Why did he not go beyond the second and third papers? After the first paper was fundamental, the second had some right ideas. And in fact, the Einstein A and B coefficients are very related to that, of there being an equilibrium between the atomic states. The reason I think that Bose got disheartened was because this was a time of very rapid movement in quantum theory. And quantum field theory was being developed at this time by the very great people like Dirac. Now, Dirac and Schrödinger and Heisenberg and all these people were at that time pumping their full energies into this. And Bose couldn't keep up with that while in Dhaka. There was no internet in those days. The physical review used to take 6 months to arrive over there. So I think that's why he then branched out into other things like looking at helium bubbling from under the ground and more realistic physics problems. So yes.
So I would like to ask Professor Ghose, on what did you work with Professor Bose?
Your PhD topic.
Yes.
My PhD topic.
Yeah.
Which problem did you work with him on?
It was vague. It was called Some Topics in Elementary Particle Physics. It's mainly about broken SU3 symmetry, some rules, various ways of deriving some rules, and so on.
Okay.
So basically on particle physics, your work is on particle.
Yeah, very much particle physics.
Okay. Yeah.
Any other questions? There's one at the back.
This is a general question from Professor Hoodbhoy and from you, Professor Partha. Which regions in India before partition were producing great scientists, like world-class scientists or physicists pre-partition? Were there any in Pakistan region, this region which is now Pakistan?
Well, I think
and in the non-Hindi speaking,
I think Professor Partha Ghose should agree. The place where I am sitting, the city where I am sitting right now, because C.V. Raman worked here. Of course, Satyendra worked in Dhaka, but his foundation happened in Calcutta. Then Meghnad Saha, Jagadish Chandra Bose. So, the Bengal Renaissance, there's the entire Bengal Renaissance influence that was working. Bengal Renaissance momentum, you can say.
Why was this the case, like non-Hindi speaking, non-Punjabi speaking? Why were they producing great scientists? Why was this particular region? That's what I want.
No, that's because, as I said, that Bengal Renaissance was something that was, it was, Calcutta was the nerve center. It was the hub of Bengal Renaissance. Okay, and C.V. Raman is not a native to Bengal, but he came to Bengal and he flourished here because he got the right kind of support. Okay, he is otherwise from south of India. Ramanujan didn't come to Bengal, but thankfully Hardy, he got noticed him and brought him to limelight. So it's mainly because that Bengal was the nerve center of nationalistic activities, and this sort of scientific flourishing is also an extension part of that nationalistic fervor. So that's the thing.
I
But
think
yeah, Punjab was also a nerve center. Now, all the actually the educational institute, which are the earliest universities that were established: Calcutta University, Bombay, and Madras. Okay, Delhi University came much later. So, if there was some center for higher learning in Lahore established at that time, so maybe there would have been scientists in Lahore too. But
Yeah,
as it
but
happened,
but there was. Salam was educated in
yes,
Lahore,
of course, yes,
but
yes.
his mathematics teacher was a Bengali from Calcutta.
Yeah, yeah.
The
but there was a
Calcuttans
very
had the
strong.
advantage. Bengal had the advantage that Calcutta was the capital of British India. And so a lot of things happened here, and the others got left out. It's very unfortunate, but I think things have reversed quite a lot.
Yeah.
Now the situation is quite different.
Yes.
But explain me one thing.
Calcutta is no longer what
Kerala
it
had
used
a,
to be. That's unfortunate.
but Partha, Kerala also had a very strong tradition in mathematics.
Yes,
What happened
tremendous
there?
tradition in
What happened there?
mathematics.
Why?
I, well, I mean, again, very difficult to answer. And mathematical researchers have shown that Kerala mathematicians did wonderful things. But somehow or other, when the British came, things fizzled out. I don't know why. I mean, you have written a book about all this. So maybe you have a better clue.
No, I haven't written a book on this at all. I want to learn, I want to understand what happened in Kerala that it didn't produce during British times great mathematicians or physicists. Anyway, let's move on to the next question. If they, yes.
Okay, I'm looking for advice, like what advice Dr. Partha and Dr. Hoodbhoy would you give to like new researchers like myself? Like we know that like scientific mind or like the true research is not encouraged in the place where we live. So what advice would you give that what can we do to like in these circumstances, what can we do?
Partha?
Advice to young scientists, young researchers.
Well, I can only relay to you the advice which is given to me by my professor. When I met him last, it must have been towards the end of 1973. I was that time teaching in a university which was founded by Rabindranath Tagore in a place called Shantiniketan. So I had come down to meet him, and he started talking to me again about Einstein and his controversies, later controversies with him. And then finally, when I got up, he came with me to the door and he said the following thing. He said, look, I find that whenever a young, brash American says something, shouts like a jackal, he said, you people all start shouting like jackals. Please don't do that. He said, try to understand everything in your one way and then try to say something new. And ever since that, I have been trying to do that. I must admit it's a very hard thing to do in today's world, where unless you follow, you jump onto the bandwagon, you are nowhere. That's the system. I think the system is not conducive to producing really original work of the kind that Bose could do at that day. Even then, even at that time, had it not been for Einstein, Bose's paper would have been just thrown into the waste paper basket. There's a lot of evidence of that.
Yeah.
So let me give you Feynman's answer to the question that you asked. Well, Feynman said, in time to come, in the next 30 years, if not 30, 50 years, as time goes on, it will be harder and harder to make breakthroughs in fundamental physics. In fact, at some point, it will become close to impossible for the human mind to comprehend all that has happened in the past, which is necessary for going on to the next step. So then one must look for branches away from what is truly fundamental towards application of the ideas that have already been discovered. And there is no limit to that. So branches will then produce further branches and it'll keep multiplying indefinitely. For this, you've got to have a trunk of knowledge. So think of it as a tree with a strong trunk. That trunk then has the capacity to sustain branching. And this is why everywhere in the world that physics is taught in graduate schools, you must learn certain things irrespective of the field that you will go into later on. I think that's excellent advice, and that's not from me, that's from Richard Feynman.
Yeah.
Okay, should we have the last question then?
My name's Aisha, and I'm actually an O-level student, so I'm pretty young, so please take my question with a grain of salt. You are retired, Dr. Hoodbhoy, Professor Hoodbhoy, but you mentioned, like in the documentary, it was mentioned how Bose realized that the problem that he was explaining to his students was incomplete because obviously he was confused as to how to explain it properly. Have you ever encountered such a problem in physics?
Not at that deep level. Yes, of course, one runs into problems, one runs into very mystifying mathematics and cannot see the way out. That's because of my limited capacity. I know, for example, that before I could think of what would happen on the route that I was traveling, my friend, who is 20 years younger than me, a Chinese physicist, could immediately see way ahead. He said, you're going to get stuck over there. And when I finally got there, I found myself stuck. And then he proposed to me a way to get out of this, and then I followed that and I was able to get it. So look, people differ hugely in terms of their capacities, their mental capacities, and that's what made Einstein, Einstein, and Schrödinger, Schrödinger, and so forth.
Very nice.
Okay, so I think we're at the end. Thank you both. Thank you, Subha. Thank you, Partha. This was wonderful. Everybody enjoyed
I
it.
would
We
like
learned a
to
lot.
thank Partha Ghose for giving that explanation of paper 2, because I have always felt that this 2024, we were celebrating Bose-Einstein statistics and we were celebrating the first paper. Nobody was celebrating the second paper. The third paper was not published at all. Okay, so Professor Partha Ghose here today gave a nice explanation of the essence of Bose's second paper. So thank you very much, Professor Ghose. So actually, we should celebrate the second paper also. The world has forgotten, but why should we forget?
Good. Any last words, Partha?
Pervez, I would like to thank you for thinking about this event and giving us the opportunity to interact with you all.
No, thank Nakhib over here. I forgot. I told you in Dhaka that I would love to have you at the black hole, but then so many things happened subsequently that it sort of slipped my mind, and then he brought it to my attention, and then of course you are here today, and I hope we'll have you again at some future time.
Let me tell you, people in Calcutta are already talking about the black hole and admiring the great work you people are doing there.
Wait, wasn't there a black hole of Calcutta?
Calcutta actually had a black hole.
Of a very different kind.
Of a different kind, yes.
Okay. Right.
Yeah.
Right. Okay, then. Thank you again, and bye.
Thank you, Professor Pervez, Professor Ghose.
Bye.
Yeah.